Hello. Today we are doing something a bit different than normal. Normally we solve practice questions, but today we're going to do a derivation. We're going to derive beta for an ideal gas. So beta is the volume expansion coefficient. And this is the textbook definition of beta. But now we're going to look at beta for an ideal gas. So first, we're going to just use the ideal gas law. So the ideal gas law, we'll start with the one that you've probably seen in chemistry class. PEV equals nRT. If not high school or college chemistry, then you've almost certainly seen it in a thermo class. So we're going to use PV equals nRT. And then we're going to actually say that volume, I'm going to use this V, just to not get confused with velocity or something. So volume is mass over density. And then what we can do is we can rearrange with mass and volume. So using these two facts here, I'll write it like this. That pressure times mass over density is equal to nRT. Perfect. But what is N? N, if you don't remember, N is the number of moles. Oh crap, moles? From high school chemistry? I hate those. So we're going to figure out how to get rid of this N. So what I'm going to do is I'm going to say that N is actually the mass over the molar mass. So M over big M. And again, we're going to do a substitution. So we still have this M over rho, but now we're going to substitute M over big M, then RT. We can divide both sides by M, and then we can solve for density. So we multiply density on both sides, and then we're going to multiply by M and divide by RT. So we get pressure times the molar mass times the gas constant times the temperature. That is the density of an ideal gas. So now we have this equation over here. You can do it in terms of volume or in terms of density. So I'm going to look at in terms of density because we just solved for density. We have this differential in here, so we're going to put this together piece by piece. So this differential d times density, the derivative of the density with respect to the temperature, we're going to treat everything else as a constant. So that's d dt of this density equation here. So pressure, mass, R. And I'm going to break it apart like this, just so we can easily see what's happening here. So all of this is a constant. We can pull that out front. And then derivatives. I'll go over here and review derivatives if we don't know how to take a derivative of this. So the derivative of 1 over x, we could rewrite this as x to the negative 1 as exponent rules. So then what we do is we subtract 1 from the exponent and then add to or multiply by that new exponent, or by the current exponent. So first we bring this down and then we subtract 1 from the exponent. So that's what we do. Bring this exponent down, subtract. So we say negative x, then you subtract 1, minus 2. So negative 1 over x squared. So that means that the derivative of density is just with respect to temperature. These are constant. Times negative 1 over temperature squared. So now we have this, and we can clean this up a little bit. Pm over R T squared, and it's a negative. Okay, but we want negative 1 over the density. So negative 1 over, hey, that's the density right there. Pm over RT times negative Pm RT squared. Well, we have density on top, density on bottom, mass on top, mass on bottom. We have R on the bottom, and we have R on the bottom of the bottom, which means it's on the top. So they cancel. And 1t cancels. These negatives, negative times a negative is a positive. And so then we're left with beta is 1 over temperature. How neat is that? So for an ideal gas, the volume expansion coefficient is 1 over temperature.